Hello again, and welcome to this second part where I'm going to let you know the basics of the scenario approach. The second part is going to be a bit more technical than the first one, so I would like to get organized this way. Right, so the title is Data-Driven Decision Making and the Scenario Approach, and we are going to concentrate on the scenario approach in this second part. To start with, this is a quote by Clive Staple-Lewis. One said, "What I like about experience is that it is such an honest thing. You may have deceived yourself, but experience is not trying to deceive you." So this really referred to experience to data, and it's very relevant to the operation of the scenario approach. So leave it there for a while. I'll come back to this quote in due course. So the scenario approach. In this presentation, I'll be focused on the case in which we do optimization. We make a decision based on optimization. Optimization is a fundamental tool to make decisions, even though it is not the only way. But as I often do in a presentation, I try to stay focused to convey ideas in a more neat way. So this may refer to whatever problem you have, MPC, which is model, predictive, control, robust control, prediction and classification. And the optimization is a fundamental tool there, because when we choose, we have a goal in mind, and not all the solutions are equally good. So we can put the solutions on a line of preference, and this leads immediately to an optimization program. So optimizing is very important when making a decision, but there is a second element that is equally important, and it is that we had to deal with uncertainty that demands exercising caution. So these two things immediately lead me to this slide where I put forward the concept of uncertain optimization. So say that you have a function j which depends on two variables, theta and delta. Theta is the optimization variables. So in a control application, for example, this may be the parameters in the controller, or in a prediction problem can be the coefficients determining a specific predictor. Delta is all the rest, is what we call uncertainty. So in my life, very rarely I've applied twice the same decision to the real world and I got the same final outcome. And this is because there are a number of other elements that are determining, together with theta, the final outcome, and all this is delta. Importantly, in applications, what theta is normally very well understood, is a crisp concept. So let's say the three parameters of a PID controller. Instead, what delta is, what the limits for delta are, and so on and so forth, how delta distributes is way more vague and difficult to understand. But for the time being, let's concentrate on the mathematical formulation of the problem. So you would like to optimize with respect to theta a function of two variables, theta and delta. And I have two observations for you. The first one is that this is not a valid mathematical formulation, or it's not a clear mathematical formulation to start with. Let me explain you why. Say that this is the axis for theta and this is the axis for delta, and that your j function is this one. So that's the j function. So if you pick this theta, let's say theta 1, you are left with this function of delta. If you pick this, you are left with a different function of delta. And there is no obvious way to compare two functions. So these are not numbers. There is no natural ordering. So you may want to adopt, for example, the worst case with respect to delta, or you want to take average with respect to delta, and so on and so forth. And that's why in uncertain optimization, there is so many diverse paradigms. So we need to be more precise than that. And the second point, which is very, very important for this talk, is that often a description of uncertainty is not available, or it is only partially available. That is, what delta is, the range of variability of delta, and so on and so forth, is not very clear to us. And this leads immediately to scenario-based knowledge. Knowledge about uncertainty can be acquired through experience. That is, we look at previous cases or scenarios of the same problem. So very often in a given application, a description about delta comes from experience. And I'd like to make this clear by way of examples. I have 3 examples for you. The first one is a predictive control. So say that here you have a linear system, very standard one, and its noise U is a control input, and that you want to minimize a cost index like this one. You have a finite time horizon n and the quadratic function in x and u. Should n be Gaussian, then this would be a standard LQG problem. So a linear system, a quadratic cost function, and a Gaussian noise, and you all know that this admits a simple analytical solution. However, let's move beyond that. Let's say I do not know what n is. The distribution of the noise is not known to me. And on top of that, I also have constraints, for example. So say that there is an f function of state and input, and the constraint is that this is less than or equal to 0, but I do not want to enforce the satisfaction of the constraints for in any situation. I just want that the probability for this to happen is more than 1 minus epsilon, and the epsilon I choose, let's say, is 1%, so the probability is at least 99%. There are many problems of this sort where you can violate, but rarely enough. There are examples, for example, in power systems, the maximum load of a power line is given, but exceeding that maximum load, even significantly rarely enough, doesn't cause any damage to the power line, or in medical applications when you control the glucose in the blood, having spikes well beyond the normal threshold is no cause of cellular damage, as long as it happens for short enough. Okay, but let's say that you have this problem here. Very typical example is when you have a given symmetric. So I do not want to give you details, but this means that the state has to belong to some polytope in the state space, and let's say that you have constraints on the inputs, that is saturation limitations. So I'll give you an example in this framework later in this presentation. One way to address this problem is to make the noise explicit with respect to the state. You assume here, you measure the state, and therefore you reconstruct the noise, and then you may want to parameterize your control policy this way. so it is affine in the noise. The good reason for doing this is that then in the end the problem becomes convex. This parameterization has been suggested first by John Ligeiros and independently in the optimization community by Arkady Nemirovsky. But here the point comes, what are scenarios in this case? Scenarios are realizations of the noise. So you refer to the past, you go on field, you collect noise realizations, and these are the scenarios for this case. And once you've got the scenarios in your hands, you may address the problem this way. You minimize your J cost subject to various constraints as given by the scenarios. So in other words, you refer to the scenarios as your wealth of knowledge about the variability of delta. I will come back to this for you later in my presentation. But my goal here is to show you that the concept of scenario is quite diverse. This is portfolio optimization quickly enough. Say that you have 100 Swiss francs in your hands, the assets in front of you to invest on. In this case, you can call PK the percentage of capital invested on asset K, 10%, 5, 15, and so on. So theta is your decision, is the vector containing the percentages. And this is a very important function. So in here you have RK, which is called in finance rate of return. So this quantifies the profit you make in investing on K. And if you multiply RK by PK, that is how much you invest on the asset K, then you have your, so to say, return for asset K. By summing over all assets, you have the return of your portfolio. So a portfolio is a selection on how to split your capital. So this function is an example of an explicit function J theta delta, where theta refers to the way you act, that is the portfolio you select, the percentages, and the delta is the profits. These are called the rate of returns for asset K. And this RK, at the time you make the investment, refers to the future. You go to the stock market, you buy assets, and then you wait until tomorrow. At the time you go again to the stock market and you collect your money. So what are scenarios in this case? These are scenarios. That is rate of returns referring to the past. So the idea is that for asset K, you have measurements, the rate of return for yesterday, the day before yesterday, 3 days back, so refers to the past. And what you can do in this case is that you plug the rate of returns into your J function. So now this function only depends on the portfolio, and this tells you how much money you would have made out of any portfolio, but in the past. And this is your wealth of knowledge. This is what you know based on the data you have. So these are scenarios. I have one more application for you. This would serve a full seminar because that's a very important application, medical application. I've been doing quite a bit of work on, but let me just touch upon this quickly. This refers to patients in cardiac arrest. So there is a patient down on ground in cardiac arrest, which is quite an extreme condition because you die in a few minutes in that condition and the brain gets destroyed by the lack of oxygen in half the time. So all guidelines, the European guideline in particular, prescribes that if a defibrillator is available, you just place the electrodes there. This is connected to a defibrillator, and you give immediately an electrical shock to the patient, in the hope that this will restore spontaneous circulation in the body. Medical experience shows that this happens only in 20% of the cases at the first electrical shock. And that's bad, because shocking someone ineffectively is a loss of time, but also it may cause further damage to the cardiac muscle. So should you know that the shock is going to be ineffective, you should not give it, and rather you should operate differently. For example, you should first give a cardiac massage, which if properly done boosts the chance that later the electrical shock will be effective. So this is a classification problem. All modern defibrillators can do two things. They can give the electrical shock, but they also collect an ECG of the patient. So this is an ECG, which is an electrocardiographic trace. So as soon as you put the electrodes, the defibrillator collects that, and the idea is that one can try to construct a classifier saying, based on the ECG, the classifier says if you shock now, the heart will restart. And it's a fundamental challenge, a medical challenge, to construct reliable classifiers to do that. The latest European guidelines have endorsed openly the fact that we are waiting for suitable classifiers having a high degree of reliability to be placed in the defibrillators, and they openly endorse the idea that more research should be done in this field to come up with such classifiers. And this is really a very important emergency, because cardiac arrest is the most important cause of sudden death in a large window for the age of the population. So what is the scenario in this case? These are data provided to us by the hospital in Brescia. So given a patient, it has an ECG, and this ECG is becomes a three-dimensional point by extracting suitable features. So one point here corresponds to an ECG, and the red means that the first electrical shock was not effective. Blue means it was effective, and based on this, the goal is to construct a classifier. So next time a patient is down on grounds, you apply the electrodes, you collect the ECG, and the patient becomes a point in here. But you have not shocked yet. And depending whether it ends in the red or in the blue region, the classifier says, yes, go ahead, shock, or no, stop, give a cardiac massage first. For the purpose of this talk, what matters is that we have seen really very diverse scenarios. Here you have a training set of the ECGs plus the outcome of the shocking and previously rate of returns, and then realizations of noise. Just to let you know that the concept of scenario is very general, is very broad. But let's go back to the main points. So here we have our j theta delta function, and from now on optimizing means minimizing, and I'm going to explain to you the operation of scenario optimization in this slide. So In my presentation, I'll be referring to the case in which the dependence on theta is convex. I should mention that the non-convex case is fully understood by now, but in the presentation I want to stay focused. So, idea is, we got data points, scenarios, and we can plug them into our J function. So one such function is this one, for example. This is another one, and you got many of those. This is what I call a bundle of functions. And this is the wealth of knowledge we have about the problem as given by our data set. So this picture is in one-dimensional in theta. Of course, you have to think much more general than that. So in general, you have many variables in theta, so this is a multidimensional object. And then this is the wealth of knowledge based on which you want to make a decision. I'm referring here to the simplest possible setup. So you can do various things, but again, for the sake of concreteness, let me refer to the simplest possible choice, which is worst case. Worst case means you first take the max over the scenarios and you take the maximum over the scenarios, and then you have this gray line, that is grain function, and then you minimize over theta. So if you do that, you end up with this decision, theta star, this is the decision, and this value, j star. So you make a selection of your decision based on what you have seen, referring back to the past, that is the scenarios. And say that this value is just a number, 273, and you know that this is good for you. 273 is a good number. Now, the question is, are we then buying this decision? Are we taking this theta star because j star is good enough for us? Just keep in mind that here we are referring to the visible part of the problem, to theta star, j star, and j star refers to the scenarios we have seen. So the way we are operating here, and this is always the case when we make a decision based on experience or observations, we first see the scenarios, and based on this we select a decision theta star, and then we also compute j star, the corresponding cost. However, the actual operation is the other way around. That is, we first select theta star, say we select a portfolio, and then we go to the stock market, we invest, and the delta materializes later, and this gives the final outcome. So this is the way it goes all the time. I make a decision, I apply this decision, and then there is an outcome as based by or as determined by uncertainty. However, in science, the decisions we make refer back to what we have seen in the past. So there is a fundamental problem in science and in scenario optimization here, and it is that we have to somehow link the past to the future. So this leads to this fundamental question: what are the guarantees for a new situation? Or more specifically, how guaranteed is J star for another delta. This is the problem of moving from the visible to the invisible, from what we have seen in the past to what we have not seen yet, referring to the future. So this is the fundamental question. This has to do with the guarantees, and I would like to provide an answer. When studying the scenario approach, we have been striving all the time for generality. If you remember from the first hour, I was telling you that a good theory should retain its validity even when certain priors you may want to use at the time you design the problem does not turn out to be correct. And now you should keep that in mind, because I would like to let you know what we have been able to achieve here. So this delta is the domain for uncertainty, so the small delta is in there, and on top of that there is a probability distribution. So I hasten to say that in this theory we assume that there is a probability distribution which governs the way data come to us. But very, very importantly, the whole theory assumes zero knowledge about this probability. So there is the real world, and the different cases come to us according to probability distribution, but I do not know what this probability distribution is. And I have various cases, delta 1, delta 2, delta 3. These are independent observations based on PR. So just to make this even more clear, what we have here on the left is the real world. The real world is quite complex. It contains a lot of aspects, is too complex for me to deal with. What I instead have on the right is the artificial world, is the way I construct my decision problem. I select J, that is what I would like to optimize, and I also select theta. So when I select a class of controller or another class of controllers, I'm selecting theta. So I manufacture the setup on the right, and after I have seen the scenarios, the setup on the right is sitting in my computer. So this is in my computer. So there is a substantial difference from what we have on the left and what we have on the right. On the left we have the real world. On the right I have the problem as I have organized it, as I have manufactured it. And throughout the theory I will try to stay away from the real world. I don't want to deal with the real world. That's too much for me. Now, tomorrow I'm going to apply my theta star, and I may see a delta corresponding to this green function. And the value is this one, which is lower than J star. So that's good. This is good for me, because the value is lower than J star. Low is good because I'm minimizing. But I may also bump into a delta case leading to a higher value, which is bad for me. So in principle, I'm not saying that in practice I'm able to do that, but in principle I can group together all red deltas, and the probability of those is called the risk. So what's the risk? The risk in this context is the probability with which my cost will be higher than J star tomorrow. And then what we are after here is to is to keep this risk under control, to give guarantees. And I want to give guarantees despite the fact that the real world is not known to me, and the probability PR in particular is not known to me. There is a first theorem dating back to 2008. This has been proven with Simone Garatti, who is the person I work with all the time. Simone is an absolutely outstanding person, a very deep thinker, and I love working with him, and I should thank him explicitly here for many years of work together. So this theorem tells us a very important fact. So let me first remove 2 lines to make it easier to read. I'm going to reinstate those 2 lines in a second. You fix an epsilon, and this is the risk parameter, say 1%. And the theorem tells us how many scenarios we need so that the risk is below 1%. This depends on epsilon, and the smaller epsilon, the larger the number of scenarios we need. Depends on D. D is the number of optimization variables, and depends on beta, and beta is in the 2 lines I have removed. So beta is called confidence parameter, and the theorem assures us that the risk is less than epsilon, but not always, with high confidence 1 minus beta. Getting a bit complicated, I know. I'm going to explain more details in a few minutes from now, but just keep in mind that when you have data, and these are picked at random, you can never be 100% sure. So there is also a confidence parameter, and the result holds true with the high confidence. But for someone using this theory, I claim that this beta is very unimportant, and the reason is that you can send this beta to very small values, say 10 to the minus 7, something that is negligible in practice. And the reason is that if you look back at the sample complexity, the beta value is under the sign of logarithm. So logarithm of 1 over 10 to the minus 7 is 16. You can take 10 to the minus 10. The logarithm is 23. So it's still a small number. So I'm going to repeat the same theorem for you in these slides. So this is the real world we have seen before. This is our computer where we perform optimization, and this is the domain for multi-samples. The theorem says somewhere there is some region in this domain such that if you pick out of it, then the theorem doesn't tell us anything. But this is a tiny small, something that is negligible, 10 to the minus 7 or 10 to the minus 10. So I forget. Then anytime I pick out of the rest, I have a problem in my computer such that I can compute the decision, the corresponding value, and I'm guaranteed that the risk is no more than epsilon. And keep in mind that epsilon we choose. So it can be 1%, 0.1%, or 5%, depends on the application. And this, of course, affects the number of scenarios we need. Few comments. And depends on how complex the decision is via D. And you see a first link here between complexity and risk. How complex the decision is via D. But N does not depend on how complex the real world is. I don't trust a theory that says if the real world is complex, you need many data points. I don't trust that. So if you ask a complex question, if you want to determine the value of very many parameters, you need very many data points. But the real world can be any complex. This doesn't enter the picture. So a message for you here is don't try to reconstruct the real world to answer easy questions. So if you go the indirect way, the indirect path, you have a complex world, you first try to reconstruct that, then you are really trying to solve a harder problem to make perhaps an easy selection. Very importantly, n is totally independent of the probability, so this is what we call a distribution-free result. And let me go back to Clydesdale-Lewis. What I like about experience is that it is such an honest thing. You may have deceived yourself, but experience is not trying to deceive you. So Lewis here is pointing to the role of experience, and using priors may deceive us. So we deceive ourselves at the time we assume things. And that's why, I'm going to repeat myself, this must impact only visible things, like remember the width of the interval, but should not have a role at the time you provide guarantees. Otherwise, you may deceive yourself. Okay, so time flies. I've given you kind of the general picture now, but I'd like to enter more in detail some results. So delving into the theory, this is going to be a bit sketchy. Of course, there are papers that you can use to understand more, and please rely on me in case you have doubts. You can email me anytime. I'll be very happy to answer your questions now or by email later. So if you go back to the paper in 2008, you see that the previous theorem is in fact a corollary to a more general result that says the risk is dominated by a beta distribution. So the risk is a probability. The risk is a probability that something bad happens. So the risk takes value between 0 and 1. But the risk is itself a random variable because it depends on the sample of scenarios. Delta 1, delta 2, delta n. For a sample of scenarios, you determine a decision, and this has a risk. For a different sample, a different decision, a different risk. So it's random variable. And this theorem says that the risk is always dominated by a beta distribution. So the distribution is like this pink line, which is a beta distribution, by the way, when d is 2, the number of optimization of variables is 2, or better than that. So the distribution is on the left, is a first order dominance. When n is 10, so half of the data points, the distribution, the beta distribution moves to the right, with the 40 moves to the left, and the previous result was obtained this way. You set an upper limit to the risk. The beta distribution is thin-tailed. You compute the probability for the tail, and this is beta. So this is the way the epsilon beta result you saw before is obtained from this result. By the way, this result is not improvable because the result is exact for fully supported problems. In other words, in the paper is shown that there is a full class of problems whose probability distribution for the risk is exactly this one, is exactly a beta distribution. So no one will ever be able to solve this problem. Let me show you what fully supported means. So we go back to this. If you remove this function corresponding to a scenario, then you improve. Same on the left. So we express this by saying there are two support scenarios. Of course, there can be less, let's say 1. and it is a theorem, the number of support scenarios is never more than d plus 1. And a fully supported problem is 1, such that the number of support scenarios is always d plus 1. Oh, by the way, this result holds true only for the convex case. So when you move to non-convex, you have to address the problem a different way. But stick to the convex, so this is a result. So this result sets an upper limit to the complexity of the solution. The number of support scenarios is the complexity of the solution. And keep in mind, very importantly, this quantity can be measured. So I give you scenarios. You put them in your computer and you determine the solution. How do you compute the number of support scenarios? You eliminate one scenario and you check whether or not the solution improves. You put back this scenario, you remove another one, and you keep going. So you remove one by one all scenarios, and you see in how many cases the solution improves. So the number of support scenarios is the complexity, and the complexity is a measurable quantity. Now, for all convex problems, there is an upper limit to the complexity, and these are called fully supported problems. And for fully supported problems, the risk is exactly a beta distribution. Let me go back. This distribution, and all other problems are dominated. So it's like this or better. Now, it is a fact that many problems are not fully supported. And for those problems, the distribution of the risk is dominated. So this is an example where you have 400 dimensions, 400 optimization variables, and 1000 data points, and this is the corresponding beta distribution. And I run a problem for you. I have computed the distribution of the risk. It turns out to be this one. And for another problem, it turns out to be this one. So it's on the left, so it's dominated. But, you know, if you use the beta distribution, you are off the real value, which is way less than what is given by the beta distribution. And this leads to a new paradigm that together with Simone we have been studying over the past 5-6 years, and it is the result in a mathematical programming paper 2019. So you take the new paradigm is taking a bivariate point of view. On this axis you have the risk. The risk is a random variable that you cannot measure in real life. On this axis you have the number of support scenarios that you can measure. This is a statistician would say a statistics of the data. And this is what we call the complexity. If you refer just to the risk, then you look at the marginal. And in this example, the margin is quite spread. However, if you take a bivariate point of view, you can first compute or measure the complexity, and based on this, you can estimate pretty well the risk. Because there is a very strong correlation between risk and complexity. Now, this picture refers to a specific concrete example. It's a real picture. In a minute, I'll tell you what it refers to. So it's a 400-dimensional convex problem where I have manufactured a probability distribution in 400 dimensions, and I have drawn 2000 data points, 2000 scenarios. Then I have taken the negative orthant. This is the origin, negative x-axis, y, z in 400 dimensions. And I push this down. That's the optimization as much as I could. by leaving all the points inside. What are the support scenarios in this case? So just in 3 dimensions are the points at the boundary. And in 3 dimensions they can be as many as 3, 1 point here, 1 here and 1 there, or as few as 1, just 1 point here. In 400 dimensions everything can happen. You can get 10 support points, 5, 150, 350. So there is a full range, as you can see from here. And based on the actual number of support scenarios in a run of the program, you can compute the risk. Risk and complexity are going hand in hand, and you can estimate the risk from a measurable quantity, which is the complexity. Now, when you find a result like this, you stop for sure and you say, how general is this? So is this a general fact or is it specific to this construction? Well, it is a fact that this fact is completely general. It holds true universally, always, always. There is a theorem here that I don't want to read in detail. Let me just show you this picture, which is a visualization of the theorem. So let me first go back here. You take an aerial view, you can draw a line here, and you can say there is nothing above this curvy line. So in other words, the risk is never above that line. This holds true universally. So this is what happens with 1000 data points. Again, that's the complexity, this is the risk. For all problems in the universe, there is very little probability mass above here, no more than 10 to the minus 6. So how do we use this result? If you experience a complexity 100, then the risk is no more than 0.16, 150, no more than, and so on. So this is a universal fact. Written in the stars, there is a link, very strong link between risk and complexity. I have a more detailed piece of information for you here. If you follow me, what I put here is the beta distribution in 200 dimensions. So this is the previous result. So say that you are optimizing in 200 dimensions. So just keep in mind that this sets an upper limit to the complexity. Because of Halley's theorem, the complexity cannot be more than 200. Right, in that case, you can take the tail of the beta distribution with the probability 10 to the minus 6, and you can claim the risk is no more than this red spot. Do not know whether you appreciate that, but the red spot is slightly below the blue spots. So if you set out to ask a question in 200 dimensions, you can make a claim which is stronger than having a question in more dimensions and then observing an answer in 200 dimensions. That's the difference between asking a question in that dimension and experiencing a posteriori that the answer is having that complexity. And then you can repeat for any complexity, you get the red versus the blue line. And you can ask a very profound question. Is the blue line getting a gap from the red because of a weakness of the theory? And the answer is no. The red line is not a feasible solution, a feasible line for the problem when you a posteriori verify the complexity of the solution. I believe this has a very fundamental epistemological value. Simple questions are more guaranteed than simple answers. However, there is very little to gain from a priori studying the problem. Wait and judge from the complexity of the solution. there are many generalizations. So all this was, referring to specific situations. So I was talking all the time of the case where you do worst case optimization. You can deliberately remove some of the scenarios to improve the solution and to play this trick to trade risk for performance. This can be done very precisely and in a guaranteed manner within the scenario approach. Everything so far has been in relation to uncertain optimization or cost functions, but you can move to optimizing under constraints, which is very relevant to us. All problems, let's say in MPC, for example, or many others are having constraints, and the non-convex case is by now understood. To conclude, let me just give you a result for the predictive control example that I've shown you in the beginning. This example is taken from a paper by, again, John Ligouros and others. These are four masses connected by springs. I'm not going to give you all the details, but the state space is in dimension 8, positions and velocities of the masses. There are three inputs, the force U1, the force U2, the force U3. There is noise, and the J function you try to optimize is basically containing the position at instant 5. So the time horizon here is 5, and you want basically that despite the presence of noise, at the end of the period, the masses are close to their nominal position. These are the constraints based on scenarios. We have n of those. This is the elongation of the springs that you want to be not too large, because you are otherwise leaving the linearity region of the springs, and this is a saturation of the input. I use the parameterization that I showed you before. So in this case we have 75 parameters. So it's optimization in 75 dimensions, and I have 1,500 data points. I solved the scenario program without any elimination of scenarios, so the min max, and the value was 0.709. Just to mention this, the LQG, J star for LQG is as low as 0.481, but just keep in mind that in that approach you do not care at all for constraints violation. And in fact, if you posteriori compute, the constraints violation is very large, 23%. I use the weight and judge. So I set the confidence parameter to 10 to the minus 6, and in this case the number of supporting constraints was 34. Oh, by the way, this problem is convex, so the largest number is this one, and it's a bit less than half. So I computed based on the previous theorem the epsilon corresponding to this complexity, and it was 94.9%. So an easy example to show you how this approach can be used within predictive control. Oh, by the way, there is more in this handbook for MPC published in 2018. So let me just say that many have taken part in this story, many groups have contributed. The scenario approach is sprawling fast, and I believe it's a fascinating worth to explore, because there is really an attempt to link the experience to knowledge, which is I believe the most important problem in science. So thank you very much. And these are people that are currently working with me on this approach. So let me just go back to full screen and just to thank the organization again, and it has been great pleasure, and I'm completely at your disposal should you have questions now or even later, and so email me, and I'll be very glad to answer your questions in case you have. So thank you very much.